Pascal's triangle. The pattern's pretty easy. We're actually starting on page 472. The pattern's obvious, right? It's almost like a Fibonacci pattern where you take the 2 before it and add it. But this is called Pascal's triangle, named after Pascal. We start with 1, 1, 1, and then you're just adding 1, 1 is 2, 1 and 2 is 3, 1 and 3 is 4, we're just doing that. That's how you create the triangle. The pattern here, though, is that this is what occurs with binomial expansion, which is what y'all did for bell work. So you can then use these as your coefficients and expand that way using whatever row you're on, all right? And so we're going to do a couple of this with Pascal's triangle. So look at example 1. A plus b to the 6th. I don't know about you, but I don't want to do that 6 times. I have zero desire to do that. And so what you'll find with Pascal's triangle is you start with your first term and you raise it to the power of whatever you're expanding. And then your coefficient for that is going to be from the 6th row of Pascal's triangle. And so if we look at right now we just have row 5, right? So we have row 5. We have to go to row 6 to expand this guy. And so to get 6, we're just going to expand it using what we know. 1 and 5 is 6. 5 and 10 is 15, 20, 15, 6, and 1, right? So to expand that to a 6th row is fine. And then your exponents are going to go down for your first one and up for your second one. All right, so what I mean by that is this is going to start at 6. This is going to start at 0. Anything to the 0 power is just 1, but we'll write it just for fun. All right, my coefficient is going to follow Pascal's triangle. So I'm going to pull that first coefficient. That's going to go there. And then I'm going to go to the next term. The next term, my A is going to go down by 1, and my B is going to go up by 1. And I am going to grab that coefficient from Pascal's triangle. Everybody see what we're doing here? All right. And then I'm going to go to my next term. And we're going to do this all the way down. My first is going to go down. My second is going to go up. My coefficient is going to come from Pascal's triangle. All right. And this is going to follow this pattern until you are finished. And you do not need to do that long foiling over and over and over again because you have now another method to do it. All right, and so this is expansion using Pascal's triangle. Now for this particular guy, pay attention to the fact that we did not have coefficients on our variables, right? So my A and my B had no coefficients. I wrote that twice, sorry. I wrote my 15 twice. This should be a 6. When you have coefficients, we're about to do one with a coefficient, then you will see that what happens is you have to expand those coefficients as well, meaning if this had a coefficient, I would have to take that into consideration when I raise it to a power, okay? But when it's just a 1, we're really simple. Now, I will say you want to simplify this. So, for example, this guy, I wouldn't write 1, A to the 6th, B to the 0. I would just write A to the 6th, right? And so you do the same thing when it has coefficients. You're going to expand the coefficients and raise them to the actual powers that you have. But your final answer would look like this. And you don't have to worry about foiling 6 times, which is, I don't know about you, but that seems a little much. That would be your answer. So if I were to take A plus B and multiply it 6 times, that is what I would get. All right? So when you have a coefficient, pay attention. This coefficient is part of a group. So you'll notice that I grouped all of these. I grouped my 2x's. I grouped my negative y's. The biggest problem here is not doing that coefficient to the power. And so you want to make sure you do those coefficients to the power and then just simplify. Positives and negative simplification there. You're just multiplying and simplifying those. So let's try one. So this sometimes feels like it's out of place because combinations just gets thrown in here. But when you do binomial theorem, which is another way to expand, you use the combination method. So first, just a reminder of what a combination is. So combination is used when you start talking about probability and statistics. Combination is used when order doesn't matter, okay? So like if I said, I need a group of you to go help move some books, and I just picked 5 of you. Order doesn't matter. That same 5 group, doesn't matter what order I put you in, is the same, right? But if I said, I have first, second, and third place in here, then order matters. Because I can pick the same 3 people and rearrange them, and they're different first, second, and third places. That's permutation. So you use the combination method, which is what we've done in the past, and you start using it to do expansion. So this is another method that is comparable to Pascal's triangle, right? You can just use combinations to do it. So first of all, what is combination? Combination N and R, what do they mean? N is the total number that you have. R is how many you're taking from that. All right? In your calculators, you should have this, but what it does is it takes the total number and does that factorial over the number that you've chosen factorial, the total minus the number that you chose factorial. All right? Factorial, remember, is like 5 times 4 times 3 times 2 times 1. It's just that number multiplied by everything below it. In your calculators, if you go into your calculator, in your calculator, you have to put in the first number first. So like A, you would put in a 6, then you would go to your probability menu and choose your combination and hit enter. And then you would put your second number and then hit enter. Okay, so you have to put first number, choose combination, second number, enter is how most calculators work. So I want to make sure y'all all know how to do it in your calculator because we're about to use it for binomial expansion. So just make sure you know how to choose your probability menu, choose your combination, put in your 6 and 2, and you should get 15. All right, so that first one you should get 15. So in your calculators, put in a 6 first, then you're going to go to, typically it's math, over to your probability menu, and down to your combination function, and hit enter. It helps to spell enter right. And then you're going to put in the second number, and you're going to hit enter again. All right, and then you should get 15. All right? If you don't remember how to do it, this guy would be 6 factorial over 2 factorial, 4 factorial. That's what he would look like. So 6 times 5 times 4 factorial over 2 times 4 factorial. Boom, boom. 30 over 2 is 15. How does this apply to binomial expansion? Well, Pascal's triangle gives you your coefficients, and so does using a combination. The combination method starts with 0 as your second number and goes up to the same number. By that I mean this example here. I am expanding to the 4th. I would use a combination of 4 and 0, then 4 and 1, then 4 and 2, then 4 and 3, then 4 and 4. What you'll find is that's going to generate the 4th row of Pascal's triangle. All right? So instead of using Pascal's triangle where I write it all out, I can just use these combinations as my coefficients and do exactly the same thing that I did using Pascal's triangle. Everything else is the same. If you were to put in C combination of 4 things taken 0 at a time, you're going to get 1. And so as you go up, if you look at Pascal's triangle, 1, 4, 6, 4, 1, that's what these combinations are going to generate. They're going to generate that 4th row of Pascal's triangle. But instead of writing out Pascal's triangle to get to the 4th row, you can use combinations. Why is this sometimes easier? Well, Pascal's triangle is all good and well when you get to like 5 or 6. But if I say 12, you're going to spend so much time writing out Pascal's triangle, right? And room for error because we're humans versus just using my combinations and what those are going to generate. Does that make sense? So it's not that you must use one method or the other. there are going to be times when one method may be easier than the other, right? And so this method here may be easier when you get to a larger one, or if you just don't even want to bother with Pascal's triangle, writing it all out, right? This is always going to work. It's going to generate Pascal's triangle for that row. Everything else is the same. I would use my first term, c cubed, and I would take it to this power, 4. And I would take my second term to d, and I would take it to this power, 0, right? That's for this one. For the next one, my c cubed is going to be taken to 4 minus 1, right? 3. And my last term is always going to be taken to this guy right there, 1. This is going to be c cubed, 4 minus 2, that's 2, 2d to the second power, 2, right? So I'm still going down for my first term, up for my second term, just like I did with Pascal's triangle. I'm just, those coefficients are being generated by my combinations versus the triangle itself. This wants me to find specific terms. This is not telling me to expand it 8 times. This is saying I want some specific terms here, all right? The first specific term they ask for is what happens when x is to the 5th power, all right? So we have to think about this. When x is to the 5th power, this whole group is going to be to the 5th power, okay? The two groups always add up to my expansion, to my degree, okay? So if this is the 5th power and I have 8 altogether, my second group is going to be to what power? To the 3rd power, all right? My coefficient is going to be the combination always of 8. The second number always follows the second term. So I can immediately pull out a specific term using the binomial expansion method. I don't have to draw out Pascal's triangle. Now you could, again, but this is 8. Combination is way faster than drawing out 8 rows of Pascal's triangle for one specific term, right? And then having to count across and figure out which term you're talking about, right? This is a much more accurate, efficient method. And then you do exactly what you would do. You would do the combination of 8 things taken 3 at a time. And I think that one is like 56 when you put it in there. So this guy right here expands to 56. Then I'm going to expand this. 2 to the 5th is 32, and I have x to the 5th. A negative to a 3rd power, that is a negative 1. So when I multiply that out, I'm going to get a negative 1,792 x to the 5th. That is the term that represents x to the 5th term. Okay? That's one way they can ask for it. They could say, when this variable is to this power, what is the whole term? All right? The second way they can ask for it is something like this. The 7th term. The 7th term. Now, so the easiest way to do this one is to think about my second term, all right? My second term goes up from 0, right? That power. So if I'm talking about the 7th term, then my second term would have started at 0 and should now be at what power? 6, right? If it's the 7th term and it started at 0, my second term should be at 6. They always add up to 8 for this guy, right? So my first term then should be at what power? 2. And my combination is always going to be 8 and follow this one. That is going to be my 7th term. Okay? Question.
So is the last term 6 because it starts at 0, so it goes 0, 1, 2, 3, 4, 5, 6?
No, the last term is going to be that to the 8th power.
I'm saying like at the bottom, like where you have the 6.
Oh,
The 7th term.
right. This, you mean the B here?
Yeah.
When it said 7th term? Yes, because the second term started at 0, 1, 2, 3, 4, 5, 6. It's always going to be one less. Altogether, you're actually going to have 9 terms, right?
Yeah.
Because it starts at 0. All right, questions on how to do that? All right. Try one. The probability. So then binomial expansion is actually used, or the concept here is used to do probability. Number of successes with independent trials, meaning they're not dependent on each other as to whether or not it is successful. if I want the probability of a specific number of successes, then I can use the combination of however many times I'm doing it, n, with the x being the number of successes I want. P is successes here. And then q, they're always going to add up to my total. So that's why it's n minus k. My number of failures, so to speak, q, is going to be what's left over between the number of attempts and how many successes I had, which makes sense, right? So Jeff randomly selects answers to 5 multiple choice questions. They each have 4 choices. Find the probability of each event. He gets exactly 3 questions correct. All right, so my combination piece here is going to be how many times that he answered. He answered 5 of them. How many successes is my second number there? 3 things taken 5 at a time. Then I want the probability of being correct. If there are 4 choices, it's a 4-choice question, and he randomly selects the question, what are the chances he gets it right? Yeah, so 1 out of 4. So we have 1 out of 4. And however many successes I want is the power that I'm going to take that particular one to. So I'm going to take that to the power of 3. So then if 1 out of 4 is his probability of a success, what's his probability of failure? 3/4. Those should always add up to what? 1, right? So 3/4. And these exponents should always add up to the total number of times that he did this. He did it 5 times. We've already used 3 of them, so this guy is going to be 2. This is the probability that he gets exactly 3 questions correct. It's a little teeny probability, by the way, when you do this. It is like 8%, I think, 0.0879. So he has an 8% probability of getting 3 questions correct, which is passing, by the way. 8.79%. That's the probability of getting 3 out of 5 correct. So look at the next one. The difference in this wording is vitally important, okay? Exactly 3 is set in stone. That's how many I want. At least 3 means that he could get 3 correct, or 4 correct, or 5 correct. So you're literally going to do these 3 and add them up, okay? So we're going to take exactly what we did here. That is at least 3. But then you have to consider the fact that he could get 4 correct, right? And so this is going to be 5 things taken 4 at a time. Now we have correct at 4 and we have failure at 1, right? And then he also, if it's at least 3, he could get all 5 of them correct, right? And so we have this at 5 and we have this failure at 0. And you simply add up those probabilities. And that's actually a greater probability, which makes sense because we have more options here. A little over 10% probability that he gets at least 3. Because now we have our 3 probability, or our 4 probability, or our 5 probability because of the wording there.